modern science began with Johannes Kepler. Johannes Kepler was the guy who in the 1600s proved beyond a shadow of doubt that the Earth and all the planets go around the sun, not the other way around. A lot of people give Nicholas Copernicus credit for this idea, and he did posit it, but Copernicus thought that the planets go around the sun in perfect circles, because circles are, as I said, perfect, and God only makes things that are perfect, ergo, the planets go in a circular path. As Professor Stubbs pointed out, this is physics, not philosophy, which means you have to look, if you have a theory, you have to look at what actually happens, compare it to your theory, and if they don't match, tough luck. And if you posit that the planets go in perfect circles around the sun, and then you look at how the planets actually move through the sky, it doesn't line up. You might as well say that the sun is going around the planets and put all the epicycles in and, explain your data. What Kepler did was he studied very detailed measurements of how the planets move, and he figured out that no, they don't go around the sun in circles, they go around the sun in ellipses. Their paths around the sun are slightly elongated. Now, if I were to draw them for you and compare them to a circle, you couldn't tell the difference, but it is there. They're slightly elongated. And furthermore, he came up with a few more rules to explain how the planets move. So, Kepler's 3 laws, which we still use today, are the planets go around the sun in ellipses. A law that can basically boil down to so because the path is an ellipse, it's slightly out of circular, which means sometimes the planet is closer to the sun than other times. And when the planet is closer to the sun, it is moving faster than when it is farther from the sun. Not by much, but just by a little. And then finally, he worked out that if you posit that for no obvious reason, if you just take the amount of time that it takes the planet to go around the sun and square that, and then take the average distance that the planet is from the sun and cube that, and divide those numbers, you always get the same result, no matter which planet you're talking about. And those 3 simple laws perfectly explain the data he had. That explains how the planets move around the sun. And furthermore, he was able to take that and figure out relatively how far all the planets are from the sun. He could use his laws and tell you that Venus is 7/10 of the distance. So take the Earth-Sun distance. Venus is 7/10 of that distance from the sun. Mars is 1.5 times as far from the sun as the Earth is. Jupiter is 5 times as far from the sun is, and so on and so forth, which is also true. You know what he couldn't tell you? How far the Earth is from the sun. Whatever that number is, he could tell you the relative distance of the planets, but there was no measurement for how far the Earth is from the sun. Now we have radar, and we can bounce a radar off the other planets, and because we know the relative distances of everything, we can tell you that the Earth-Sun distance, which we call the astronomical unit, is, I had to write this down, 92,955,807.2 miles. That's very, very far. That's why you can't measure it. You can't lay down a stick and say, how long is my stick? Because it's 92 million miles. Well, 93 million miles. So this is in the 1600s. Fast forward to 1716. Edmund Halley, the guy with the comet, is observing the transit of Mercury. And what that is that's just when Mercury is passing between the Earth and the sun, such that if you were to look at the sun through a filter, don't ever do that, you would see a black dot passing in front of the face of the sun, because you would see Mercury's shadow moving across the sun. And he realized that if he could observe a transit of Venus, he could figure out the Earth-Sun distance. And he would do it by using a phenomenon astronomers call parallax. What parallax is so I'll give you an example. If I stand here, I can see the gentleman with the sunglasses on his ball cap. I can see his head over the gentleman with the America shirt. If I now lower my head, the gentleman with the America shirt is totally blocking the gentleman with the sunglasses. It's not because either of them moved, it's because my perspective moved. And what Halley figured out is if he can get him and his astronomer buddies to measure the transit of Venus from 2 different positions on the Earth, he can measure that relative change in position. And that gives him an angle. And then he knows the distance from Venus to the Earth, because we know that Venus, in astronomical units, so he knows that, there's 3/10 of an astronomical unit between Venus and Earth. So that gives him 2 arms of a triangle. And then he just needs the distance between the 2 astronomers to complete the triangle. And because that's a distance on the Earth, we actually can measure that one. And so now you have an angle over here, and you have a distance we've measured over here, and you can do geometry, and you can get this distance from Earth to Venus. And because you know that Earth and Venus are separated by 0.3 astronomical units, you can then get the astronomical units. So, yay! The problem is Venus is very uncooperative. Transits of Venus are transits of Venus are kind of odd. They happen 8 years apart. Except after those 2 that are 8 years apart, it's 100 plus years until the next one. So you have 2 chances in 8 years, and then your grandchildren are doing it. So Halley figured this out in 1716. And the next transits of Venus were in 1761 and 1769. Halley died in 1742. So Halley didn't get to do this. But the astronomical community remained aware of his plan. And so when 1761 rolled around, they mobilized. Like half a dozen astronomers went to half a dozen different locations to try to measure the transit of Venus. And they did it again in 1769. And they made these precise measurements of the relative positions of Venus on the sun. Actually, they did it by timing how long it took Venus to cross the face of the sun. That was an easier measurement, but they were able to back it out with geometry. And then in 1771, an English astronomer named Thomas Hornsby calculated that the Earth to Sun distance, the astronomical unit, was 93,726,900 miles. Remember, the correct number is 92,955,807.2 miles. They were within 1% of the correct answer using just telescopes and clocks. Yeah. So, I mean, I just find this fascinating. Like, all of these, astronomy is really hard because it's all so far away. But you know, if you're clever enough and dedicated enough, you can measure that even without modern tools like, you know, the radar. So, yeah, they were kind of awesome back then. Thank you.